Okay, a little lesson on calculating the rate of reaction, the rate of chemical reactions. And we can calculate the rate of reaction with respect to different reagents. So in other words, we can look at how quickly different reagents are being used up or consumed, or we can calculate the rate of reaction based on products. So we can look at how individual products, how quickly they are produced. So probably the first thing to realize, since we will not solve these problems in a vacuum, but we'll solve these problems, with respect to real world scenarios, is how do we measure rate in the lab? Because we're going to be looking at working with data from laboratory scenarios, and it's really helpful if we can contextualize, like, how is this data produced, and how does this data actually show us rate of reaction? So one really common method we use to measure rate in the lab is we look at mass change. Okay, so usually in this case there's gas being lost from the system. So gas is like produced as a product, and then it no longer contributes to the mass of the system because it's lost to the room in an open system. So we can measure the mass of gas lost over time. Remember, rate is always like the change in something, as you can see here, the change in something over time. So we have to, in this case, measure the mass of gas lost over time. We could possibly also measure the mass of some other thing that's lost, like maybe some aqueous component, but it's a little bit more tricky. It's most commonly a gas being lost. We could also look at the volume of gas produced. So one way we do this, for example, that you often see is they'll have a little like reaction vessel happening over here. So the reaction will be happening in a flask, okay? And then that flask is actually stoppered, okay? So it seals in anything produced. And then there's a hose running into like a big beaker, like this. That's adjacent to it, like that. And then there'd be like an inverted cylinder inverted in that beaker, which will be able to collect the gas as it bubbles out, okay? So that you'll be able to read the scale here, okay? You'll be able to read this little scale and see what the volume of gas is produced over time by this reaction, okay? If that makes sense. So it's called collection of gas over water. So collection of gas over water, I think, is kind of a fun process, and you can use it to quantify the volume of gas produced over time. You may also have some reactions that can do a color change. They might become cloudy, or they may produce some colored product, or they may consume some colored reagent, so they become more or less colorless. And you might say, well, how do we measure that? You can measure it with a device called a spectrophotometer. Okay, spectrophotometer. What a spectrophotometer does is it basically tests how difficult it is for light to pass through a sample. So it can tell you about the intensity of color in there because of the difference in opacity or transparency of a sample. You can also do, this is something, again, which technology has helped us in vastly over the last 20 years, but you can also do photographic analysis, or basically like photos extracted from a video over time analysis, and evaluate like the pixelation and the intensity of color in the images and the pixelation, and from that you could see how quickly color is being consumed or produced. So this is kind of a cool technology application there. And then finally, although you may not understand much about it at this stage, like you can have a pH change as a reaction occurs, because there could be more or less acid or base being produced or consumed as the reaction happens, right? So you might see like pH decrease if you were to measure it with like litmus paper or a pH probe. You may see the pH decrease or increase as a reaction progresses, and it depends on the nature of the reactants and products in that case. Okay, so here's an example that we'll dive into on calculating the rate of reaction. So It says, in a particular chemical reaction, the rate can be explored by measuring the mass of hydrogen produced over time. Okay, and then it gives you the balanced chemical equation there. There could be a point in the future where, depending on the reaction at hand, you may have to come up with the chemical equation and balance it yourself, but in this case, it's given. So the reaction is, as you can see here, we have aluminum metal reacting with HCl, which is hydrochloric acid. So it's a metal acid reaction producing a salt, aluminum chloride, and hydrogen gas. Then you can see the setup here, the experimental setup on the left-hand side, where on a mass balance, there's the cord for the mass balance. It's plugged in. You know, mass balance is a fancy word for a scale, like a digital scale. So on a mass balance, we are conducting this reaction in a flask. We mix the stuff together. Aluminum, see the little aluminum solid in there, and then we've got the HCl, aqueous HCl in there, and it's producing hydrogen gas, which is escaping. And so we're taking data from that here, and the data collected over time shows that we can take the mass of the system over time, and of course the mass decreases over time because the hydrogen gas right here is escaping. Okay, and so notice that, you know, we may say stage A, B, and C. Notice that the mass is decreasing every single time, and you may also notice that the mass decrease actually slows as we go, and this is what we generally expect for a reaction. We would assume it is supposed to be fast at the start and then slower as we go, okay? And that's because there is less reagent left, or less concentration of reagent or reactant as a reaction progresses, and so it should happen more slowly, and we'll hopefully continue to consider that sort of trend as we go. Anyways, the question is this: calculate the rate of aluminum consumption in grams of aluminum per minute between 30 seconds and 60 seconds. So we're basically looking at between point B and point C. You know, to put it in other terms, this is kind of defining the period over which we want to see how fast the aluminum is used up. Okay, so let's take a look at this. Okay, what are we going to do? How are we going to tackle this? Well, the first thing we can put in is we can calculate the rate from 30 to 60. It's going to be the mass change, okay, which is going to be, you know, remember that a change is always final minus initial, okay? So it'd be like the final mass minus the initial mass, generally speaking. If we do that, it's going to give us a negative number in this case between points B and C, right? It's much easier with rates if you always just work with it in the positive. And although it seems like kind of strange to force something negative into something positive, in chemistry we'll know based on the context whether it's consumption or production. And in this case, it's clearly consumption. We're using the word like, what's the rate of consumption, right? So we can go ahead and just keep it in the positive. To me, it makes a little more sense. You can work in the negative if you'd like, but you should just understand at the end of the day, it's reagent consumed. Okay, so here we go. We'll put our final units. Our goal is to get it in grams of aluminum per minute. That's our goal. All right. Let's see what we do have. And I would highly encourage you to write down the units in detail as you go. It'll really help you see where you are in the process, because we're going to stack up conversion factors. Okay, so we're going to take these masses, big one minus the little one, because that's the way I want it. I guess I did it backwards anyways. Doesn't matter. Here, I'm going to switch it just to make it, do it my way. The 200 minus the 270.170. This is grams of something. Let's figure out what it's grams of. That's really important. Over time, 60 minus 30. Okay. So what is it actually mass of? Well, hopefully you realize that it's mass of hydrogen being lost. Okay. The mass is going down because the gas is being lost from the system. Nothing else could really be lost. It's all going to stay in the flask, you know, unless there's error, like there's, or I should say mistake, like there's spatterings of liquid. But by and large, this should just be the mass of hydrogen. So let's put it in there. It's grams of hydrogen That's really important to help us, like, or to help me at least, stay organized. So if we do the math on that, we now have our units are grams of hydrogen per second being consumed. Okay. What we really are aiming at, though, is aluminum, right? We need to aim at grams of aluminum produced. So how do we convert from hydrogen back to the reagent of aluminum? You should realize that any time you need to make that translation, reagent to reagent, reagent to product, product to product, product to reactant, you have to use moles, right? So right now we have this in grams. We have to convert it to moles. So let's transfer this to moles of hydrogen per second rather than grams of hydrogen per second and start there. So we know we get 1 mole of hydrogen gas for every 2 grams of hydrogen. That's using the relative formula mass, right? So now we've got our units in moles of hydrogen, okay? After that, we're going to use our conversion factor of there's 2 moles of aluminum for every 3 moles of hydrogen. And if you're wondering where that came from, that comes from the stoichiometry of the reaction, right? So we have the 2 as the coefficient there and the 3 as the coefficient on hydrogen. And so it's produced at a 2 to 3 rate, okay? And that's just what we're going to use. All right. Next factor. So now we... Oops, I'm getting my pen sorted out here. Okay. So now we have it in moles of aluminum per second, right? That's currently our unit. We are going to stack up some more conversions here. So we don't need it in moles of aluminum. We need it in grams of aluminum. So use the relative formula mass of aluminum. It's 27 grams per mole. Cross out, cross out. That will now put our value into grams of aluminum per second. But of course, what the question is asking for is grams of aluminum per minute. So now we're just going to multiply by the conversion factor to cancel out the seconds. So there's 60 seconds in every 1 minute. Remember, it's per minute, so you want minute on the bottom. Seconds will cancel out on the top. If you do all the math there, punch it all in your calculator, it should work out to be 0.54 grams of aluminum per minute. Okay? 2 significant figures is all I put on that. I probably should have put a third on there, because if you look at all the given data, I think it's all given in 3, isn't it? So let's adjust this to, I think it works out to be 0.540 grams of aluminum per minute. Hopefully that last digit's correct. Again, one last comment. Don't get too hung up. If you look at this, you might say, hey, here you did 60 minus 30, you did C minus B, but up here you did, the 0.2 minus the 0.17, that's B minus C. What am I up to here? Remember, I'm just trying to say, really, for rate, use absolute value. I think it's easier to keep it positive. All right, here's another one. If 3.6 grams of copper solid is used up every minute in this process below, and, here's the process, what mass of NO2 gas will be made after 180 seconds? Okay, so what we basically have here is we have grams of copper per minute. Okay, that's this reagent right here. And we need to convert it to mass of NO2. So we're going to look at grams of NO2. Again, I'm going to write this down as, I call it like a target. We're going to get to grams of NO2 after 180 seconds. So let's go for grams of NO2 per second, and then we can multiply it by 180. Yeah, and that seems reasonable. All right, so we have 3.6 grams of copper produced per minute, or sorry, not produced, but consumed per minute, right? So again, we have to translate, or we have to convert from copper over to NO2, nitrogen dioxide. to do that conversion, we will have to get to the standard of moles, right? Moles can build the bridge, so we have to get this to moles. So let's translate this to moles. So what's the conversion factor, or the relative formula? Mass, 63.55 grams of copper for every 1 mole of copper. That'll take us to moles of copper per minute. Okay. Now let's use the conversion factor. It looks like, according to the balanced chemical equation, which we are thankfully given, that you get 2 moles of NO2 for every 1 mole of copper. Of course, there'd be a 1 there. So it's going to be a 2 to 1. 2 moles of NO2 for every 1 mole of copper. That will get us 2 moles of NO2 per minute. All right. Then, of course, it actually asks for the mass of NO2, so let's convert that to mass. So if you look at the relative formula mass, it's 46.0 grams of NO2. Again, this is from the periodic table, per every mole. Cancel, cancel. We are now in grams of NO2 per minute. Okay, so let's get that into the per second value. All right, since that's what ultimately we're aiming at here. So we have 1 minute on the top, and we have 60 seconds on the bottom, canceling out minutes. Now we have it in grams of NO2 per second, and if we just take that value and times it by 180, then we'll have how much is produced in 180 seconds, right? The actual mass. And another way to look at that is to say, like, okay, 100 times 180 seconds. So we'll get our actual just final mass after 180 seconds. If you do all the math, beep, 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 punch that into your miraculator, you're going to get 15.6 grams. Take a look at the data that you're given. We are actually given data in the limited precision of 3.6 grams. So we better just answer as 16 grams. Okay? So we would have 16 grams of NO2 lost or produced after 180 seconds.